Hello and welcome to my talk on predicting length of stay with temporal pointwise convolutional networks. I'm Emma Rosto, a PhD student and medical student at Cambridge, and this is work in collaboration with Pietro Leo and Stephanie Hyland. I'll start with why we want to predict length of stay. So firstly, the longer the patient stays in intensive care, the higher the cost. And secondly, longer stays increase the risk of getting a hospital-acquired infection, such as multiple drug-resistant bacteria or COVID-19. We can mitigate for these by streamlining patients through the hospital with improved bed management, but this requires knowing how long the current set of patients are going to remain in the ICU, so we can plan for their discharge, avoid bottlenecks, and prepare the incoming patients. In our work, we use electronic health record data from the eICU and MIMIC4 datasets, each of which contains thousands of ICU stays from various hospitals across the US. Both datasets contain time series, which includes vital signs such as heart rates, which are constantly logged by machines, and also lab results, which are irregularly sampled and can have large time gaps between the measurements. You can see the difference on the right. So the top three are parameters, are vital sign parameters, whereas the bottom three are lab results. And it's important that we design our model such that it can cope with both types of data. We also have demographics, diagnoses, and medications, but our work focuses on extracting better representations from the time series specifically. Broadly, we want the model to extract both trends over time and also the relationships between features, just like clinicians do in their decision-making. This is made clearer with an example. So if we imagine that we have a coronavirus patient who has lung failure, a clinician would want to know how the lungs are doing over time by looking at things like the blood oxygen, which is shown in red as PaO2 here. They'd also like to know how these values are changing over time. So if the PaO2 isn't improving, then the clinician might predict a long length of stay because it's going to take time to wean this patient off of their ventilator. Another thing to consider is how the blood oxygen interacts with other features, such as the fractional inspired oxygen, shown as FiO2 in blue. So the blood oxygen could be high just because the patient is breathing in a lot of supplemental oxygen, not because they're actually doing better. So we want the model to be able to infer these relationships as well to gain a more accurate representation of the health state. To extract the trend information, we use temporal convolution. An example time series is shown along the bottom, and we can see that as we go through the network, the convolutional filters are dilated more and more until we have an output neuron that's able to extract a trend over the entire patient's stay. And when we add skip connections, we can see that the network can now choose to alter the temporal receptive field, or in other words, the time period over which it can look backwards. And this is useful because for vital signs like blood pressure, it may be useful to look at the recent history, whereas for lab values, the short-term trend might be completely useless since they're unlikely to change over such a short timescale. To extract the interfeature relationships, we use pointwise convolution. So the aim here isn't to pull information across time, but instead to look at all of the information that we have at a given time point and then extract a high level feature from that can be some combination of the input features. This diagram shows how we combine the two methods in parallel. So on the left, we have the temporal branch, and the separate colors blue and green indicate that we use different convolutional filters to process each feature. And we do this because of the huge variation in the behavior of different features. So it makes sense that the model should have the freedom to model each independently. And on the pointwise side, the model takes everything that we know from a given time point and then computes high-level features from that. And then the two are combined with concatenation, and the process can be repeated many times as these layers can be stacked. So moving on to some results. On the left in blue, I'm showing the mean squared log error, which is our loss function. And on the right in red, we have the mean absolute percentage error, which is a more interpretable metric. And along the bottom, we first have a median model that will always predict the median value no matter what the input data is. And this just shows the performance available by predicting a reasonable range. And the next three are baselines, which have been shown to perform well in the literature, but our TPC model does significantly better than all of these methods. And this impressive performance is repeated on the MIMIC4 dataset, except that the performance boost is even more profound here. Next, we tested whether the TPC performance could generalize to other patient outcome tasks like mortality prediction. And again, we were able to outperform the baselines by the area under the receiver operating characteristic and precision recall curves. And this performance benefit was repeated on MIMIC4. It's not shown here, but we found that by combining the two tasks together in a multitask way, we were able to boost the TPC performance again on length of stay by 10 to 15%. So we wanted to understand better why the TPC model is doing so well. So we performed some ablation studies and we found that the temporal convolution contributes more to the performance than the pointwise convolution, but the best performance is only gained when they're used together. So they must be somewhat complementary in the information that they extract. And when we removed the skip connections from the temporal convolution, the performance decreased by about 15%. And when the model was forced to share weights when processing each feature, the performance degraded by more than 50%. And this shows that it's incredibly important to consider how your data is varying between the features and to allow the model to have the flexibility to be able to cope with that. So to summarize why our TPC model performs so well on EHR time series, it's been specifically designed to extract trends and interfeature relationships. And it can theoretically choose its own temporal receptor field size because of the skip connections. And that choice can be different for each feature because the parameters are independent. And finally, because the temporal convolutional filters are rigid in their spacing, this allows us to exploit periodicity in the EHR time series due to sleep-wake cycles, medication schedules, daily lab tests, and meal times, etc., in a way that LSTMs and transformers can't. So that's the end of my talk. So thank you for listening, and thank you to my funders and my wonderful co-authors, Pietro Leo and Stephanie Highland.